This is the last of our 4 lectures on inflation. We've already seen how inflation manages to launch the universe's expansion in just the right way, solving the flatness, horizon and monopole problems. And last lecture, we also learned how it solves the structure problem. It takes tiny quantum fluctuations, turns them into real fluctuations, and then blows them up huge, where they become the seed roughness that ultimately spawns stars and galaxies. In this lecture, I want to explore another feature of inflation. Its stunning creativity. By the end of this lecture, your head will be spinning at the possibilities. Now, there are actually 2 somewhat different aspects of inflation's creativity that I'm going to be talking about. First, inflation makes our universe out of almost nothing. And second, inflation is actually capable of creating many universes, not just ours. So as you can see, these are not small topics. And I've just got half an hour, so let's get started. So I want to begin with a rather obvious fact. The universe contains an enormous amount of stuff. I mean, just think about it. It's already impossible to imagine just how much matter is inside the Earth, let alone the Sun or a galaxy or the billions of galaxies that we see with telescopes. If we add it all up, everything, out to our cosmic horizon, we get about 10 to the power 53 kilograms of matter, a truly mind-numbing amount. So here's a question. Where did it all come from? How did the Big Bang manage to make all this stuff? Or was it somehow already there at the beginning, waiting to emerge? Or was it created out of nothing, ex nihilo, to use the theological term? This last option seems to violate one of the cherished ideas of physics, namely the conservation of energy, that expressly forbids creation of something out of nothing. Well, before we get too tangled up here, let's slow down and remember that we've not yet included everything in our sum. We've forgotten to include the gravitational energy of the universe. So let's look at all this now a bit more carefully. Here's a simplified Newtonian analysis that gets the result we're after. Think of the visible universe as a huge sphere of density ρ and radius r. The radius is roughly the speed of light times the age of the universe, about 14 billion light years. But because the age of the universe is roughly 1 over the Hubble constant, we can write r as c over h. The density, of course, is our old friend, the critical density, 3h squared over 8 pi g. So, the total mass in the visible universe is just the volume of the sphere, 4/3 pi r cubed, times the density, ρ. So if we plug in our formulae for ρ and r, we get this neat little equation. The mass of the visible universe is roughly c cubed over hg, which, if we plug in the numbers, gives us our humongous mass, 10 to the 53 kilograms. Well, so far, so good. But what about the sphere's gravitational energy? It's given by this formula, minus gm squared over r. Remember from lecture 12, it's crucial that the gravitational energy is negative. Okay, so just plugging in our other equations, we get a gravitational energy, E grav, of minus c cubed over hg times c squared. Now notice I've written this in the form of Einstein's famous E equals m times c squared, where the equivalent mass in the gravitational energy is c cubed over hg, which is the same number we had before, only negative, minus 10 to the 53 kilograms. Now don't worry if you didn't follow that algebra. The bottom line is that the matter and gravitational energy have equal and opposite values, so they add up to 0. This is an extraordinary realization, and it takes a second or two to sink in. What I'm saying is that all that you see around you, the staggering abundance of matter and energy everywhere, is only the positive side of reality. There is an equal and opposite negative side that resides in the gravitational fields that permeate the universe, out between the galaxies. If you could somehow perceive those fields and fold them together in your mind with all the positive mass, you would see that the total was nothing. It sums to zero. Now, it's not that everything is an illusion. You and I do exist, but our mass has been made by borrowing energy from gravity. In fact, let's use that metaphor for a moment. If you go to a bank, penniless, and take out a simple loan, you can go and buy things: a house, a car, furniture. These are real things, and it looks as though you're nicely solvent. But in truth, you're not. Your net worth is still zero. You have an exactly equal and opposite debt sitting in the bank. Now, for the universe, the debt is the gravitational field, and you and I and the Earth and stars are all borrowed against it. Do you see how this now shifts our question of where did all the matter in the universe come from to a rather different question? How did the universe split nothing into positive matter and negative gravity? How was the bank able to make this loan? Now, the answer, as I'm sure you've guessed, is that inflation does exactly this. But before we get to inflation, I want to remind you that we've already encountered this topic before back in lecture 12, when we talked about how dark energy produces an accelerating expansion. So let me briefly review that now. Here's our sphere, radius r and mass m. It has a gravitational energy of roughly minus gm squared over r. Now, if that sphere contains normal matter and it expands, the mass stays the same, but since r increases, then, looking at the equation, you can see that the gravitational energy gets smaller and more positive. But remember, more positive energy is uphill, and more negative energy is downhill. So an expanding sphere of normal matter is moving uphill. In other words, let the sphere go from rest and it falls inwards, just as you would expect. But, and this is the important part, if the sphere contains vacuum energy, which doesn't change with expansion, then when the sphere expands, although r increases, m also gets bigger, and the overall gravitational energy gets larger and more negative. So for a sphere of vacuum, then, expansion is downhill, and that's why vacuum-dominated universes fall outwards and accelerate. Well, so far so good, but there must be more to the story, because if the sphere gets bigger, there is more vacuum in that shell, and its mass must have come from somewhere. Well, it comes from the gravitational energy released as the sphere falls outwards. We have the extraordinary situation in which the very thing that is falling outwards, the vacuum, is able to make more of itself as it falls. Do you see now that this is our bank loan mechanism? As the gravitational energy gets more and more negative, as the debt grows, more and more vacuum is created. The money pours out of the bank. This is an energy-conserving process. The debt and the loan are always equal and opposite. Their sum is always zero. And this has got to be one of the most amazing phenomena in all of physics. It's an incredibly elegant mechanism to create limitless amounts of vacuum and limitless amounts of gravitational energy out of nothing. Now, this mechanism seems to have occurred in nature in two rather different contexts. The one we've met before is dark energy, with very low vacuum energy of today, which falls outwards very, very gently. But the other time this mechanism occurs was during inflation. And in that context, the process was incredibly fast and powerful. Remember, back in the very early universe, the vacuum that drives inflation is extremely dense. And in a split second, the entire bank loan is made. We have a huge amount of freshly made dense vacuum and an equally huge amount of negative gravitational energy. Now, after inflation, remember, the vacuum energy changes to radiation and matter, and we're off and running. The entire mass energy content of the universe has been made, and it's expanding at the escape speed with Euclidean geometry. The process is a thing of sheer beauty and economy. However, at this point, there is one final possible fly in the ointment that I need to tell you about. To actually start the expansion, we need a minimum amount of vacuum, a seed patch, if you like, to get the process off and running. It's actually not too difficult to see why. Going back to our sphere, if it expands to add this shell, the extra gravitational energy released is gm sphere m shell over r. And this must be at least as much as m shell c squared in order to make the extra shell. Notice that the m shells cancel, so for inflation to get going, we need gm sphere over r to be greater than c squared. Basically, you need a big enough sphere to generate enough gravitational energy to create the new shell. Now, I won't go through the algebra, but you can recast this condition in two equivalent ways. Either the sphere's size must be larger than the speed of light times the expansion doubling time, or the sphere's mass must be larger than the expansion doubling time in seconds multiplied by 10 to the 35 kilograms. Once we have a seed patch this big or this massive, inflation will take care of everything else. The region will keep falling outwards and quickly generate enough material to make the entire universe and more. So how big do these seed patches need to be? Well, for inflation near the gut transition, the doubling time is about 10 to the minus 36 seconds, giving a seed size 10 trillion times smaller than a proton, weighing about 100 grams, about as much as this apple. So it's not quite true to say that our universe was generated from nothing. We need about an apple's worth of mass to start the creation process going. But once going, remember, inflation is extraordinarily powerful. In just 10 to the minus 34 seconds, that tiny seed has grown to be 100 meters across and weighs 10 to the 88 kilograms, ample for making the universe we live in. Now, this need for a seed patch of vacuum to initiate inflation raises an extremely important topic, the pre-inflation universe. What was present before inflation? What environment might have made a patch of dense vacuum that then inflated? Actually, the honest answer is that we really don't know. If the theory of inflation is already on the outskirts of our understanding, then the pre-inflation universe is definitely beyond. As usual, that doesn't mean, of course, that there aren't many ideas about that time. There are, and I want to tell you about some of them. But it's important to stress that this next topic is much more speculative than almost everything else in the course. So let's use this diagram to introduce the pre-inflation universe. It's a standard diagram of the size or scale factor of the universe plotted against time, but with exponential axes, spanning a huge 60 powers of 10 along each axis. Moving from right to left, we go from today's universe filled with galaxies, to the microwave background, to the pre-1 second universe with its lepton and quark eras, And here's the incredible jump in size during inflation. Now, in this diagram, I chose to put inflation at 10 to the minus 36 seconds, lasting about 100 doubling times. But it may not have been then, and it may have been much more than 100 doubling times. Now you can see the pre-inflation region, just to the left of 10 to the minus 36 seconds. Notice all the question marks pointing to this region. We are entering a twilight realm where little, if anything, is known for certain. This also reminds us that we need to be extremely careful when using everyday concepts to think about this era. For example, if time itself somehow emerged from this realm, then questions such as what happened before have no meaning, because the word before already assumes a prior time. Now, actually, we really don't know whether time emerged here or whether there was, in fact, a prior time. What cosmologists often do, and is done in this diagram, is simply extend the time axis backwards before inflation by a factor of about 10 to the 7, at which point they draw a curtain of deep uncertainty at 10 to the minus 43 seconds, the Planck time. At this time, one is approaching, in a sense, nature's inherent graininess. 10 to the minus 43 seconds is just one tick of nature's clock. And the scale of the horizon, 10 to the minus 33 centimeters, is the granularity of space itself. Space and time are no longer smooth in this era, so our normal theories of physics simply don't apply. Now, actually, as you may already know, what's sorely missing from our toolkit is a theory that manages to combine Einstein's theory of gravity with quantum mechanics. And it's a project that's been a holy grail of physics for almost half a century. There have been several approaches, and although none have fully succeeded, many physicists are optimistic that string theory, or its newer version, M theory, will ultimately provide a solution. As you might imagine, string theory's primary aim is to understand the vacuum, because it's deep down in the vacuum that everything happens. That's where all the laws of physics reside. That's the medium in which particle collisions occur and the forces are made known. In fact, in string theory, particles actually are tiny strings that vibrate across minute regions of the vacuum, and the particular pattern and mode of vibration defines which particle it is. In string theory, space also takes on a new form. This image shows a projection into three-dimensional form of a tiny nugget of space with curled up higher dimensions. They're called Calabi-Yau spaces, and it's across them that the strings wiggle and vibrate. Hidden in its three large dimensions, at every location of space lurk 6 other dimensions that are wrapped up and tiny. Something that is extremely difficult to imagine. One popular idea among string theorists is that one of the defining moments in the pre-inflation realm involved the collapse of those extra dimensions, a process called compactification. 3 dimensions remained large, while 6 or 7 in M theory curled up to make the Calabi-Yau spaces. One of the most interesting aspects of this compactification is that the precise way in which the spaces curled up, the precise shape of these Calabi-Yau spaces, then defines the laws of physics and the particular set of elementary particles. So this was the moment at which the laws of physics that we now have were stamped into the vacuum. This was when the true character of our universe was minted. Now, quite how we get from the Planck realm to the launch of inflation is really not known. In fact, there may not even be this simple time interval as shown here. So rather than pretend we can smoothly bridge the two, I'm simply going to jump to the topic of starting inflation. Although many cosmologists have worked on these issues, the two whose names are perhaps most associated with launching inflation are Andrei Linde and Alex Vilenkin. Remember, to get inflation started, we need a seed region of dense vacuum. If inflation is at the gut transition, that seed might weigh as much as an apple. If it's closer to the Planck time, then it weighs more like a grain of sand. So how do we generate these regions of dense vacuum? One possibility is called chaotic inflation. There is a pre-inflation realm with a writhing sea of quantum fields, and within this sea, the most extreme quantum fluctuations make seed regions that are large enough to inflate, and one of these becomes our universe. Now, this introduces two rather profound ideas. The first is that our universe may have resulted from a random quantum fluctuation. And this raises the remarkable possibility that the birth of our universe may have had no explicit cause. Remember, quantum fluctuations are profoundly random. So the normal backwards chain of cause and effect may get broken by the quantum fluctuation that triggered inflation. Maybe there was no ultimate cause for the universe. It just happened. The second, perhaps even more stunning possibility is that other quantum fluctuations may make other universes. In other words, our universe may be only one of many in what has come to be called the multiverse. This illustrates the pre-inflation realm with its various regions, some of which spawn universes and others don't. And here's an illustration of the post-inflation multiverse. Both these are higher dimensional projections. The curved surfaces represent the curved three-dimensional volume. Our visible universe would be a small, approximately flat part of one of these regions. But beyond our horizon might lie many other universes, including some that are completely separate with no connecting bridge. Now, before we take a closer look at this really amazing idea, I want to introduce the second major development in the theory of inflation, and it's called eternal inflation. This idea zeroes in on the fact that the vacuum that drives inflation is constantly fluctuating. Here's our diagram of the ball rolling down the hill that mimics the evolution of the energy in the vacuum's scalar field. The quantum fluctuations mean that the ball is jittering back and forth slightly as the field energy goes up and down. So although the ball might be slowly rolling down the hill for most regions, for a few regions, the quantum fluctuation will keep the ball high. But, and this is the important part, the regions where the ball is high expand faster because they have higher energy. And relative to all the other regions, they gain in total volume. But inside these new volumes, the same thing happens. And this keeps repeating. And ultimately, there is always somewhere that keeps inflating. This diagram illustrates, rather schematically, the situation. As time moves from left to right, an inflating region spawns other inflations, which spawn yet other inflations. And so it goes on and on, eternally. Along the way, a multitude of universes is created, and there are always more being formed. Now, I hardly need to point out that this is a rather large idea, and one with a number of implications, so let's take a moment to think about them. First of all, we need to recognize that our universe may be only one of many, perhaps exponentially many, that make up the multiverse. Now, you could be forgiven for thinking that this is just absurdly extravagant. So let's just reflect on that gut response for a minute. For example, if you accept that inflation launched our universe, for which there's growing evidence that it did, then the simple additional idea that it simply can't stop itself isn't too much extra to swallow. Also, I think we should remember that the history of cosmology is one of ever larger boundaries. For centuries, the universe was just the solar system. Then it was realized that stars were distant suns, and the universe suddenly got much bigger. Then it was realized that the nebulae were distant galaxies, and again the universe got even bigger. So now it seems our universe may be just one of many universes, and perhaps in time that idea will feel no stranger than the idea that there are many galaxies in the universe. Now, this eternal inflation also changes our sense of the past and the future. For example, when you learned that dark energy makes the future of our universe look a little bleak and lonely, were you disappointed? And if so, how do you now react to the possibility that entirely new universes are being born right now and will continue to be born forever? So while our universe may become bleak and dead, the multiverse continues to thrive. Our idea of the past also changes. We no longer see our Big Bang as the beginning. It's just one in a long line of inflationary launches that goes back and back. Now, you might think that this removes the need for a beginning, but it turns out not to be the case. Some rather subtle reasoning suggests that there must have been some starting point, some original Big Bang that got the whole thing going. Unfortunately, of course, that sort of meta-origin is now so removed from us that it's utterly beyond observation, and who knows, possibly beyond theory too. In fact, this may also be true for the other universes in the multiverse. They're just not observable, and this makes some cosmologists rather dubious about the whole idea. After all, if something can never be observed even in principle, is it still part of science? Well, other cosmologists take a more positive view, saying that as long as the theory is robust and well supported, then even if it predicts things you can't see, that's still okay. It's a bit like atomic theory in the late 19th century. It was so robust and well supported that scientists didn't need to actually see atoms to feel very sure that they existed. Finally, one of the most intriguing possibilities is that each universe is born with different laws of physics, which might depend on the particular way that higher dimensions compactify to define the vacuum. Well, we'll return to this whole topic of many universes, each with its own physical laws, in the next lecture, when we look at why we have our particular set of physics laws. Let me briefly review. This lecture had two parts. The first was a relatively well-understood look at how inflation manages to create this massive universe. It borrows energy from gravity as it falls outwards during inflation. For every positive kilogram of matter in you and me, there is a negative kilogram of gravitational energy out between the galaxies. The ultimate origin of the matter in your body was during inflation, as a balance to gravity. It was an energy conserving process that ensured your mass was made. We also learned that inflation needs a seed patch of dense vacuum to get going, not much. At the gut epoch, we only need about an apple's worth of matter in a region 1 trillion times smaller than a proton. Now, the second half of this lecture looked at how such seeds might form in the pre-inflation universe. It's important to recognize that our knowledge of this time is extremely uncertain, and what is desperately needed is a quantum theory of gravity, of which string theory and M theory are perhaps our best current bets, although it still is far from complete. We looked at two models for the start of inflation, the so-called chaotic and eternal models, and these raise two extraordinary possibilities. First, that random quantum fluctuations may have created the seed patches, and second, that quantum fluctuations during inflation can cause at least some portions to keep inflating forever. Both these ideas led to the extraordinary possibility that there may be multiple universes in addition to our own. So just like the ancients, who struggled to accept that the stars were in fact extremely distant suns, perhaps in time we will need to accept that our entire universe is a tiny part of all of physical reality that includes many, possibly an infinite number, of other universes to make up the multiverse. Inflation, as the title of this lecture suggests, turns out to be stunningly creative.